All right, hello. Today we are going to talk about Chapter 12. And in Chapter 12, we're moving from hydrocarbons. So remember in Chapter 10 and Chapter 11, we were dealing with just the hydrocarbon group of organic molecules. And within the hydrocarbons, we had alkanes, alkenes, alkynes, and aromatics. Now we're going to do a switch to some new functional groups. These ones I'm going to focus on today have the element oxygen and sulfur in them. So the three I'm looking at are going to be the alcohols, the ether, and the thiol functional groups. So alcohols they're going to have this hydroxyl group attached to, now remember the R variable is standing for a group of an alkyl group, so just a group of carbon and hydrogens, okay? So an alcohol contains the hydroxyl group, I do want you to know that, so get that memorized, attached to a carbon chain. So in this particular picture, they're showing us water. Water is not an organic molecule. Okay, they're just focusing on the fact that if you start off with water and you replace one of these hydrogens with a carbon, now you've made an organic molecule. So all you need is one carbon with its hydrogens and then a hydroxyl group, and that'll be your simplest alcohol. A phenol, so this is another word I want you to know, contains a hydroxyl group attached to a benzene ring. So these are the two types of alcohols we're going to work with this chapter. So if you see the OH group, you know it's an alcohol. If it happens to be attached to a benzene ring, then it has a special name. It's still an alcohol, but it has a more common name called phenol. So naming alcohols, I'm going to be keeping the alcohol structures for you simple to name. And then this is going to end the naming of our organic compounds. So I'm going to take you through a lot of different functional groups, but the only ones I'm going to expect you to be able to name are the alkanes, alkenes, and some simple alcohols. So naming the alcohols, you are going to you're going to name it just like you do your alkanes, but you're going to erase the E and replace that with an OL. So, and then also the names of alcohols will have some common names. So there's two different naming systems. We're going to be naming using the IUPAC system, but some alcohols have a common name. So for alcohols, I want you to be able to do both, the common name and the IUPAC name. So in the common system, you use the name of the alkyl group. So you name your carbon chain, and then you just follow it with the word alcohol. So here's an example. Starting off with methane. So CH4 is just our simple alkane methane. If I remove one of these hydrogens and I put on a hydroxyl group, that's going to, instead of being methane, it's going to drop the E and add OL, so it's going to turn it into methanol. In the common system, you just name your carbon group as a branch. So it would be methyl, ending with YL because we're treating it like a branch. And then you just put on the word alcohol. So methyl alcohol is an alcohol with one carbon. If we focus on ethane, this is just our simple, an alkane. So it has two carbons, so it's ethane. If I replace one of the hydrogens with a hydroxyl group, it's going to change from ethane to ethanol. In the common system, we would name it ethyl alcohol. Okay, so be able to do both of those. Here, 3 carbons. Once you get to 3 carbons or more, you need to use a number on the parent chain to let the reader know where the hydroxyl group is found. So in this first one right here, I've got 3 carbons, and the OH is on the first carbon, because we would number from the side closest to the OH. So this is going to be 1 propanol. When it ends with OL, it lets the reader know it's an alcohol with a hydroxyl group. The number 1 lets the reader know what carbon that hydroxyl group is found on. The common name for this would just be propyl alcohol or N-propyl alcohol. So that N stands for the fact it's just a straight chain, 3 carbons in a straight chain. If I move on to this next alcohol, the longest chain is 3 carbons, so it's going to be like a propane. We're going to drop the E and add all, so this is also a propanol, but the OH group, the hydroxyl group, is found on carbon 2 in this one. So this would be 2-propanol. So make sure you can see the difference between 1-propanol and 2-propanol. And then the common name, remember if we're going to name this as a branch, so I'm going to go up to this one. We would name, if we're working on the common system, you name this as a branch. So this would be propyl, and then you would just put on the word alcohol, propyl alcohol. This branch right here also has 3 carbons. So it is going to be a propyl. But remember when we talked about, I gave you that picture of the tree with the 2 different branches, and one branch just had 3 carbons in a row, and that was propyl, but one of the other branches was a branched branch, and so it had 2 carbons with 1 carbon coming off of it, and that was isopropyl. So this would be considered isopropyl alcohol. So more names of alcohols. So for alcohols with 3 or more carbons, the position of the hydroxyl group must be indicated by using a number. So the IUPAC names for longer chain, you're going to number the chain from the end nearest the hydroxyl group. So in this particular example, this would be carbon 1. We would number from right to left because the I hit the hydroxyl group sooner if I make this carbon 1. If I had started from left to right, the hydroxyl group would be on carbon 3. We wouldn't want that. In this particular example, I would number from left to right, so I can hit that hydroxyl group quicker. So that's why this is a 2, the 2 because the hydroxyl group is on carbon 2. Bute because there's 4 carbons in my longest chain, and it ends with OL, letting the reader know that there's a hydroxyl group. And this one right here, you're going to number, if you see an OH group, you're going to number from the side nearest the OH group, not from your nearest branch. Okay, so we would number from right to left on this one. And you end up, once again, you're going to end it with OL because it has an OH group. Hex because it's got 6 carbons in your longest chain. 2 because the hydroxyl group is on carbon 2. And 5-methyl tells me that there is a methyl branch on carbon 5. Okay, so once you get the alkane rules down, these other rules don't add too much more complication. So here's a learning check. Name this particular molecule. So step 1, let's find our longest chain. Longest carbon chain is going to be 5 carbons, so it's going to be pentane. But instead of being pentane, I'm going to drop the E and add OL. Now I need to let the reader know where that OH group is found. So I'm going to number my parent chain from the side closest to the OH. So that would be reading it from left to right this time. So here's carbon 1, 2, 3, 4, 5. So my hydroxyl group is found on carbon 2. So I'm going to say this is 2-pentanol. Now I need to let the reader know that there is a methyl group off of carbon 3. So 3-methyl, 2-pentanol. Okay, so that's about as complicated as our naming is going to get. The next 3 slides, I'm just going to take you through some common, typical alcohols you might come in contact with. I'm not going to test you on any of these, so you can just kind of sit back and enjoy the next couple slides. Methanol is a common alcohol. It has this abbreviation MEOH. Also, the common name would be methyl alcohol, and it's also known as wood alcohol. It's poisonous. Ingestion may lead to blindness and death. It is the raw material for the production of formaldehyde, which is needed in the plastic industry. So if you are in a business where you use formaldehyde, here is the, oh no, this isn't. So that's one of the reasons, it's one of the things we use methanol for. It's used as a solvent, denaturant for ethanol, and it's also used as the fuel for sterno. So if you've ever cooked using that tub of sterno, that is uses methanol. Denaturant for ethanol, ethanol is the beverage alcohol. So if you own a factory or something that uses ethanol as a solvent, but you don't want your employees drinking it, you can add methanol to it as a way of poisoning it so that nobody will drink the ethanol. And it's a good solvent. And it's produced, one of the ways of producing it is to take carbon monoxide, react it with hydrogen under very high pressure and very high temperatures, and then a catalyst. So that's one of the ways of making it. Ethanol, here abbreviated ETOH, common name ethyl alcohol, also called grain alcohol. This is produced by the fermentation of sugars or by the acid catalyzed hydration of ethylene. So that should be sounding a little more familiar because we talked about hydrogenation of alkanes. It's used as a disinfectant. It's in solvents. It's a good solvent, so it's good for dissolving things. Many of your extracts have ethanol in it. So for example, your vanilla extract, used in perfumes and lotions. It is also the beverage alcohol. 2-propanol, also called isopropyl alcohol. This is the common alcohol that you have if it's like the rubbing alcohol, if you're going to disinfect something. So used as your rubbing alcohol, back rubs, disinfectant. 1,2-ethane-diol, also called ethylene glycol. I'm not going to take you this deep into naming alcohols, but just out of interest here, when you see the prefix di in front of the OL, that lets a reader know that there's 2 OH groups, 2 hydroxyl groups. And then since there's 2 hydroxyl groups, we see 2 numbers out here letting the reader know where to find those 2 hydroxyl groups. So 1,2-ethane-diol is used in the production of polyester. You also find it in antifreeze. 1,3-propane-diol. So once again, this has two hydroxyl groups, also called propylene glycol, used in antifreeze. 1,2,3-propane-triol. So here we have tri, meaning there's 3 hydroxy groups, found on carbon 1, 2, and 3. This one is also called glycerin or glycerol. It's the syrupy liquid used as a moisturizing agent in a lot of your cosmetics. We use it in labs for inserting glassware into tubings where it's really stiff, so you need it lubricated to slide it in. So I'm not going to test you on any of these typical common alcohols you might come in contact with. I just thought it was interesting. Pretty soon we're going to be getting into some biochemistry, and one of the chapters focus on carbohydrates or sugars. And if you look at some of the simple sugars here, you can see that a sugar has a whole lot of hydroxyl groups. So it's just another common one. So polyhydroxyl, aldehydes, and ketones. So we'll be getting to these pretty soon. Okay, switching gears to some chemical reactions that alcohols go through. There's going to be 3 we're going to focus on. Complete combustion, which we've already talked about in the last chapter, but alcohols also go through complete combustion. Alcohols go through dehydration, and then we're going to talk about redox reactions with alcohols. So oxidation and reduction reactions. Okay, combustion. Alcohols undergo combustion with oxygen to produce carbon dioxide and water. Here is a reaction showing methanol. This isn't a very good picture to go along with this, because when you're doing flambés, they are not using methanol, they're using ethanol. But this picture, the actual formula is looking at methanol and reacting it to oxygen. So remember, combustion is when something burns in oxygen, and complete combustion is going to produce carbon dioxide, water, and heat. Now you don't ever have to write the word heat in there, but this is an exothermic reaction when an alcohol is combusting. So you have to remember that. Combustion, add oxygen and produce carbon dioxide and water. So that's the first reaction of alcohols, is combustion. The second reaction is the dehydration of an alcohol. Now remember, when we were doing alkenes, we did hydration, where you added water to the alkene. In a dehydration reaction, we're going to remove water. So dehydration is going to form an alkene. This is the opposite of addition of water to an alkene. So start off with our alcohol. I'm writing it in a special way here, where I've taken one of the hydroxyl group and then the neighboring carbon, I've put a hydrogen up to show the roping off of the water, because we want to dehydrate. In order for this reaction to happen, it's going to need an acid catalyst. So there's going to be an acid above the arrow. It might just be, grab the pen instead of the mouse. You might just see a hydrogen ion up here instead of the actual acid. But for dehydration to occur, you've got to have an acid catalyst, and then you have to have heat. So it's good for you to memorize that this triangle over an arrow means heat needs to be added to this reaction for this reaction to occur. Okay, so we're going to take off the hydroxyl group, and then you're going to take off a hydrogen from a neighboring carbon. That's one of the hard things to remember with dehydration. You are not going to take off one of these other hydrogens bonded to the carbon that contains the hydroxyl. Okay, so if we take off the hydroxyl group from this carbon, that's breaking this carbon's octet. So it is looking to make another bond. And then if I take off a hydrogen from a neighboring carbon, it breaks this carbon's octet. So the way these two carbons resatisfy their octet is to make a double bond between them. Okay? And then don't forget to write your water out here. So water is the other product that forms in a dehydration reaction. So alcohols undergo dehydration when heated with an acid catalyst. The loss of hydrogen and then OH from adjacent carbons. That's important to remember. So I have my two carbons. I take off a hydroxyl group from one carbon, and then I just find any adjacent carbon. There is a rule that goes along with this. Remember, I told you the last lecture to ignore any reference to Markovnikov's rule and how to add when you're hydrating. There's a rule to which carbon gets the hydrogen and which carbon gets the hydroxyl group, but we're not going to go that deep into it in this class. So just ignore any reference to it being important, which adjacent carbon you steal a hydrogen from. I'm going to try hard to always give you a symmetrical molecule, so it won't matter which carbon you take the hydrogen from. I need to rephrase that. It is important which carbon you take the hydrogen from. It does need to be an adjacent carbon to the carbon that you take the hydroxyl group off. So this carbon right here is the carbon that I'm stealing the hydroxyl group from. So I just need to go to a carbon either to the left or to the right of it to steal a hydrogen. Well, in this example, I don't have a carbon to the right. So the only neighboring carbon in this example is this one here to the left. So I'm going to steal that hydrogen. And so that's where I'm going to get my water. So I put my water down. When I take off this H and the OH, I break this carbon's octet, so I have to put a double bond between those two. Notice, if you're doing a note card, I recommend doing an alcohol on one side of the note card, doing an alcohol with the acid catalyst and the heat, and then on the back, write down alkene. So an alcohol, when it reacts with this stuff here, and then on the back of the card, write alkene. So you have one note card with the names, and then have another note card with the actual molecules, so you can try practicing if you can get the right products. Once again, I will always give you what's over the arrow. You just need to be able to write the products. So here's a learning check. See if you guys can do this one. I'm going to take off, once I see that I've got an alcohol. Now you're just going to memorize there's three reactions for alcohols. Combustion. Now this is not a combustion reaction because we would see oxygen being added. Or dehydration, or oxidation reduction, which I haven't talked about yet. But you're going to know that I want you to do dehydration if you see an acid and heat. This arrow, this triangle right here is kind of a dead giveaway for the fact I want you to do dehydration. It's the only reaction that you're going to see the triangle over, okay? But you also need to know that that triangle means heat, because I might write heat over the arrow. So I'm going to do dehydration. I'm going to take off water. So I know right off the bat, if you want to get some partial credit, you're going to add water over here. So I know part of the water molecule is going to come from this, taking off this hydroxyl group. Now, what carbon which carbon just lost its octet when I've taken off this OH? That's this carbon. This carbon is now unhappy and it's looking for something to bond to. So what we're going to do is we're going to make an adjacent carbon unhappy. Okay? So we've got two choices. We've got a carbon here on the left and a carbon on the right, and it doesn't matter which one you do. So I'm just going to take one of these hydrogens and put it up here for us, and I'm going to turn this into a CH2. Okay? So I'm going to take off this hydrogen. Now I have just broken this carbon's octet. So to resatisfy their octet, they're going to make a double bond between them. So this CH2 is going to double bond to this CH. So I'm going to have a CH2 double bonded to a CH. And then I'm just going to bring this last CH3 that I didn't end up touching. Okay? So it doesn't matter. I have the double bond here on the left. You could have it here between these last two carbons. Either one's fine because I gave you a symmetrical molecule. Okay, oxidation and reduction reaction. So this is the last one you need to know for alcohols. Redox is the abbreviation we use for oxidation reduction. In an oxidation, there is an increase in the number of carbon-oxygen bonds. Remember from previously in inorganic chemistry, there was three ways you were going to know oxidation happened. Loss of electrons, gain of oxygen, or loss of hydrogens. Okay. In inorganic chemistry, we did a lot with the losing or gaining electrons. But now that we're in organic chemistry and when we get to biochemistry, those molecules, it's easier to identify what's reduced and what's oxidized by following the oxygens and the hydrogens. So if there's an increase in the number of carbon and oxygen bonds, then that's going to indicate oxidation has happened. Or if there's a loss of hydrogen, that would be an oxidation. So the opposite is going to be true for reduction. A decrease in oxygen, or a gain or increase in hydrogen. Okay, so just that's a refresher for you. So oxidation of alcohols. I'm just going to show the oxidation part. And in this particular case with alcohols, we're going to remove 2 hydrogens. So gaining of oxygen or loss of two hydrogens. Here is my alcohol. We know it's an alcohol because this R just means it's a bunch of carbon and hydrogens, an alkyl group. Here's a carbon that's typically usually summed up in that R variable. But here's my OH. So this is my alcohol. We are going to symbolize an oxidizing agent with this oxygen in brackets. So you're going to want to make note of that. This symbol right here means you have an oxidizing agent. And the oxidizing agents are going to be the agents that are either going to remove the 2 hydrogens or add an oxygen. So if you have an alcohol with an oxidizing agent, I want you to memorize that you're going to remove 2 hydrogens. So we're going to take off these 2 hydrogens. Now you have to pay close attention to which 2 hydrogens you take off. So one of the hydrogens is going to be the hydrogen that's part of the hydroxyl group. Okay, so find your OH group and strip off one of those hydrogens. Now what atom have you just broken the octet of? Yeah, which atom have we just now made mad because we've taken something off of it? That's the oxygen. So oxygen, since it doesn't have its octet anymore, is looking to bond to something. So we want to make a neighboring atom mad so that the oxygen can bond to it. So what is the neighboring atom? There's only going to be one neighboring atom in this scenario, and that is always going to be the carbon that is bonded to the hydroxyl group. So when you are doing oxidation of an alcohol, take the hydrogen off the hydroxyl group and then take the next hydrogen off of the carbon that is bonded to the hydroxyl group. I know that's a lot, so you just have to kind of practice that. So when you take those 2 hydrogens off, you've broken the octet of this carbon and this oxygen, so the way they resatisfy their octet is to put a double bond between them. And then that brings them back to 8 electrons. Organic structures don't tend to show the correct Lewis structure, so you're not seeing these lone or non-bonded electron pairs. This right here is an aldehyde. I haven't talked about aldehydes yet, so bear with me. I'm going to take you just a little bit further along just so that your brain can see it a couple times. When I teach you reactions of aldehydes, I'm going to teach you that aldehydes can also be oxidized, just like alcohols. But in this scenario, here's my oxidizing agent. This time, instead of removing 2 hydrogens, we're going to add an oxygen. So for aldehydes, you need to learn where that oxygen is going to be added. And it's always going to end up going between the carbon and the hydrogen. Here, you find the carbon that has the double bond oxygen on it, and then you find the hydrogen that's attached to it, and you're going to slip an oxygen in between that carbon and hydrogen. So I'll talk about that a little bit in a few more slides or on the next lecture. But I wanted to stress that sometimes when you see this oxidizing agent here, the oxygen with brackets, I want your brain to say, when I see that guy, I'm either going to remove 2 hydrogens or I'm going to add an oxygen. So you have to pay close attention to what functional group is on the left side of the arrow. If it's an alcohol, remove 2 hydrogens. If it's an aldehyde, you're going to add an oxygen. Okay, so oxidation of alcohol. So in this last example, notice that my alcohol produced an aldehyde. Okay, in this next example, my alcohol here, I should be showing you the oxidizing agent. So I have an alcohol. I know it's an alcohol because here's my OH group. I see my oxidizing agent, which tells me I'm going to remove 2 hydrogens. I take off the hydrogen that is attached to the hydroxyl group and then a hydrogen that is attached to the carbon that's bonded to that oxygen. And then I'm going to make a double bond here between the carbon and the oxygen. In this particular case, we're going to get a ketone. So the difference is how many R groups are bonded to the carbon. This carbon here has 2 R groups, so that leads us to a ketone. Back here, in this alcohol, we only had 1 R group. So that's why we end up getting an aldehyde. You don't even have to worry about that, okay? You don't need to look at whether your alcohol has got 1 alkyl group or 2 alkyl groups. I just wanted to point out that, you know, sometimes you get aldehydes and sometimes you get a ketone out of the product. This particular alcohol, however, has got 3 R groups on it. So if we tried to oxidize this alcohol, so we know it's an alcohol because here's the hydroxyl group. We see this oxidizing agent, so we say, okay, we're going to take off 2 hydrogens. I know one of the hydrogens we're going to take off is bonded to the oxygen, and the second hydrogen is going to be bonded to the carbon that's bonded to the oxygen. Well, does this carbon have a hydrogen? It doesn't. So in this particular case, we cannot oxidize this alcohol. So you're going to write just no reaction as your product, because we cannot do a reaction because there's no hydrogen on this carbon to steal. Okay, so keep that in mind. Some of your alcohols you cannot oxidize, and some of them you can. So here is a learning check. Select the product for the oxidation of this particular alcohol. So pause the video, see if you can do this. I see the oxidizing agent here, so I'm going to say, okay, I'm either going to remove 2 hydrogens or add an oxygen on. So I have to pull out my information sheet and see what functional group I'm dealing with here. When I see this hydroxyl group, that tells me that this is an alcohol. And you're going to have memorized that when you oxidize an alcohol, you take off 2 hydrogens. So we have to think about which hydrogens we're going to take off. Well, the first one's easy. It's the hydrogen on the hydroxyl group. The second one is the hard one. This one is, and it helps me to think about whose octet did I just break. When I take this hydrogen off, this oxygen now is unhappy and it's looking for a bond. Well, where is it going to bond? The only place it can bond is to put another bond to this carbon. So before I can make a double bond to this carbon, I better make it mad by removing a hydrogen off of them. So these are the 2 hydrogens that we're going to take off. So we're going to be left with this ketone. It has a carbon double bond oxygen, which would be number 2. So this would be the correct answer for the oxidation of that alcohol. Here's another learning check. Select the products when 1-propanol undergoes each of the following reactions. So here's the alcohol we're looking at. What is the product if you see this arrow with heat and acid right after it? Well, I want you to memorize. When you see this over the arrow, you are going to do dehydration. When you see the oxygen in brackets, that means you're going to do oxidation. When you see this alcohol with oxygen added to it, that's going to be combustion. So once you have that memorized, you also kind of need to think about what you're going to do. Dehydration, you are going to subtract water off of it. Oxidation, you're going to subtract 2 hydrogens. Combustion, you're going to produce, so the products are going to be carbon dioxide and water. Okay, so if I take, let's see how it's best to do this. Let's just put an A, B, and C out here by the numbers by which one A, B, and C goes with. So the products, if I dehydrate, well, I'm going to take off water. So I'm going to take off this OH, and since I'm making this carbon mad, I have to come over to a neighboring carbon and take off one of these H's. And then I'm going to end up with a double bond between these 2 carbons. So that's going to lead me to an alkene. So that would be number 1. So A is going to lead me to this alkene product. I could also just memorize dehydration of an alcohol gives me an alkene. If I oxidize, I have to remove 2 hydrogens. So this is going to be the hydrogen. This hydrogen I'm going to remove when I take off 2 hydrogens. And then I have to take off this one, because I have to remove the next hydrogen from the carbon that's bonded to the oxygen, and then a double bond is going to occur between this carbon and the oxygen. So that's going to lead me to a carbonyl group, a carbon double bond oxygen. So that would be 3. So reaction B is going to lead me to this product. And then we already said combustion is just always going to produce carbon dioxide and water, so that would be number 2. So there is a summary of the 3 reactions you need to have memorized for alcohols. So some biological Dehydration. So dehydration reactions are known to occur in many important biological processes. The Krebs cycle, which you're going to learn about in either biology or anatomy and physiology, I'm not sure which one hits that, but you'll be learning about the Krebs cycle. It is part of the process living organisms use to oxidize carbohydrates to produce energy. And it's a pretty complicated cycle that you'll get to learn. But one of the steps in the Krebs cycle, it actually does this oxidation where let me look at this here for a second. We have got a hydrogen here. So I said oxidation, but it's actually reduction, right? Or it's actually going to be dehydration, because here's my alcohol. And if I notice, the difference between this first structure and the second structure is that I have this double bond here. So which reaction takes me from an alcohol to an alkene? That's the dehydration. So they've taken off this OH and they've taken off one of these hydrogens here, and they've made the double bond. So that's dehydration. And then what happens in the next step is it hydrates again. It puts that water back on. But in this time, when they break that double bond right here and they add something back to these two carbons, this time the water is added in the opposite direction, where the hydroxyl group is on this carbon and the hydrogen is up here. This particular molecule is a secondary alcohol, which is more easily oxidized in the Krebs cycle. So it does this dehydration and hydration step to get to a molecule that's more easily oxidized. So citrate is a non-oxidizable alcohol. So the conversion to isocitrate by dehydration followed by hydration is necessary in the cycle to continue. So if we went back to why is it, if I were to ask you why is it that citrate is not oxidizable, I would want you to say, well, if I wanted to oxidize this molecule, I would take off this hydrogen, and then I'd want to take off a hydrogen on this carbon. Well, is there a hydrogen on this carbon? There's not. So I can't not oxidize this molecule. So going through this hydration, dehydration step gets you to an alcohol that you can oxidize, because this carbon does have a hydrogen that you can take off when you want to oxidize it. So I'm not going to ask you anything that's complicated. I'm going to save this for the biologist to teach you about the Krebs cycle, but it's just kind of an interesting note, I think. A little bit about the phenol. So remember, a phenol is a benzene ring right here, benzene attached to the hydroxyl group. So benzene, or phenol, is the IUPAC name for benzene with a hydroxyl group. It's used in antiseptics and disinfectants. So here's just a couple examples. Mainly, I just want you to be able to recognize it as a phenol. If you have a big structure and I'm asking you to identify all the functional groups, if you see a benzene ring with an OH, you can identify that as phenol. You could also identify it as an alcohol and an aromatic. Okay, so those are two different ways of identifying the functional groups of phenol. Derivatives of phenol. So compounds of phenol are active ingredients in the essential oils of cloves, vanilla, nutmeg, and mint. It's out there in a lot of compounds you find in nature, but just make sure you can identify the phenol. The benzene ring with that OH group is your phenol. Pretty soon you're going to be able to identify a bunch of different functional groups in these molecules. So I won't test you on any of the information on this slide. It's just kind of interesting to see it. Okay, so I'm finished. That just finishes up the functional group alcohols. I'm now going to go into ethers, and I'll finish up with thiols. So you're going to recognize an ether when you have an oxygen with carbons on each side. So an ether contains an oxygen between two carbons. It has a common name that gives the alkyl names of the attached groups followed by the word ether. So I'm not going to test you on the namings. Okay, remember, I'm not going to ask you to name ether. But what I am going to do is when I go through each functional group, I am going to tell you a little bit about how it's named, just so that you can identify which functional group that you're dealing with from the name. Okay, so the way the IUPAC system for naming an ether is a little bit more complicated. So what I'm going to show you here is just the common way of naming ether. So what they do to name an ether is they look at the R groups on each side and they name it as if it's a branch. So here I have two methyl groups. So we would call it di for the two methyl groups, dimethyl, and then you just finish it off with the word ether. Over here, this group, you tell me it's got two carbons, so what is the name of this branch? Two carbons would be eth, and since it's a branch, it's ethyl. This one here, this branch is one carbon, so it's methyl. And then we name it alphabetically, so we'd go ethyl, methyl, ether. So that's the common way of naming an ether. I'm not going to ask you to name an ether, but it's good to be able to see the name and have some idea of what functional group you're dealing with. Properties of ethers, so like your alkanes, they do not react with most reagents. So because of that, they're not a very reactant molecule. So we use them often as solvents. Many behave as anesthetics. Like many organic compounds, ethers are flammable, so they will go through combustion, like most of your organic compounds will. So some anesthetics, they inhibit the pain signal to the brain. Anesthetics like diethyl ether were used over a century but caused nausea and were flammable. So there is diethyl ether. Developed in the 1960s, the new ethers, anesthetics developed in the 1960s were non-flammable, so here's just a couple of them that are used nowadays. I am not going to ask you any of these specific questions, so it would be good to know that ethers are used as anesthetics. MTBE is an example of an ester. It is methyl tert butyl ether. So some of you may have heard about this. This is a pretty popular compound. So here is the methyl group. This group right here, I'm not asking you to name a branch. This is one more of those branched branches sort of a thing. So this is called tert butyl. The but comes from the fact the branch contains 4 carbons. So I wouldn't expect you to name this. What I would expect you to be able to do is look at this molecule and tell me it's an ether, because you have a carbon, here's an oxygen, and another carbon. Okay, so be able to identify this as an ether. MTBE is second in production of most of of all the organic compounds produced. This one is your second most in production. It's an additive used to improve gasoline performance, so it helps with the octane rating of gasoline. Its use has been questioned since the discovery that MTBE has contaminated water supplies. So many states have banned MTBE from being an additive in the fuel. They were discovering that it's very soluble in water, so it was leaking out of some of the pipes and contaminating the water supplies. So some states have recently banned MTBE. So this is just kind of a note for a little bit of trivia. So basically just be able to identify your ethers. The last functional group we're going to look at on this lecture is the thiols. You will recognize a thiol because it has this SH group in it. So alcohols have an OH group, your hydroxyl. Thiols will have an SH group. So thiols are compounds that contain that SH group. They're named in the IUPAC system by adding the word thiol to the alkane name with the longest carbon chain. So basically just find your longest carbon chain, name that as an alkane, and plop the word thiol at the end. So here's an example. I see the sulfur hydrogen, so I find the alkyl group. This alkyl group just has 1 carbon, so it's methane thiol. This alkyl group right here has 2 carbons, so it would be ethane thiol. So just name the alkane part just as if it was an alkane ending with the word thiol. I'm not going to ask you to name thiols, just be able to recognize if you see an SH on the molecule, be able to identify it as a thiol. Thiols often have strong odors. They're used to detect gas leaks. So when you cook with gas or natural gas, that is an odorless gas, but it's toxic. So what they do is they put a couple sulfur compounds into the gas so that you can smell if you have a gas leak in your home or business. So thiols are the molecules that they use to give it the smell. They're often found in onions, oysters, and garlic. So these are some good examples of letting you know, thiols usually have a pretty strong distinctive odor. Reagent bottles are often labeled as stench. So if you go back into a chemical stock room, usually you'd see the word stench written on a lot of your thiol bottles, letting you know that if you're going to do a reaction with this thiol, you're going to want to be in a fume hood. I already mentioned this, added to natural gas to produce an observable odor. Here are the two thiols that they add to the natural gas. So methane thiol and ethane thiol are the two to give it the odor. It is found in skunk spray. So if you get sprayed by a skunk, it's that thiol you're smelling. So before I go into the reactions of thiols, so far, what do I want you to know about thiols? I want you to be able to identify them because of the SH. And I want you to know that they have very strong odors. The only reaction you have to deal with thiols is the oxidation. So your brain should be saying, okay, I wonder if it's going to be the addition of one oxygen or the loss of two hydrogens, okay? And for thiols, you're going to want to memorize that it is the loss of the hydrogen. So when thiols undergo oxidation, a hydrogen atom is lost from each of two thiols. So this is a little bit different. You haven't seen this yet. But in order for thiols to be oxidized, you need two different molecules. When we oxidized an alcohol, we just plucked two hydrogens off of one alcohol molecule. But to oxidize thiols, we need two. So here's one of the thiols and here's the other thiol. And we want to take two hydrogens, so we take one hydrogen off of each one. Now when we've taken this hydrogen off, we've broken the octet of sulfur on each one. So what happens to resatisfy their octet is the two sulfur atoms will bond together. Okay? So when you oxidize a thiol, two molecules, strip a hydrogen from each one, and then bond those two molecules together to make one molecule. The product is called a disulfide. So the prefix di meaning two, and the sulfide meaning you've got two sulfurs bonded together. I do want you to know that. Okay? So when you oxidize a thiol, you're going to be producing a disulfide. Oxidation of thiols helps explain cross-linking in proteins. So for example, hair permanence. So this is kind of a fun side note. In proteins, we're going to be talking about proteins are built up of amino acids, and you have one amino acid that is a thiol. It contains a sulfur and a hydrogen. And those amino acids will cross-link some of your proteins by making that disulfide bond. So we'll talk more about that when we get to biochemistry. But right now I just want you to be able to, I'm going to give you some real simple thiols, and I want you to be able to show me the product of those two thiol reactions. So here I'm showing a generic thiol. I wouldn't be able to name this because we're just using that generic R, which means it's a group of carbons and hydrogens. So when you take a thiol, two of them, and you oxidize it, you're going to get your disulfide. So I've already talked about that. The opposite of that reaction happens if I reduced it. If I took a disulfide and I reduced it, then I'm going to go this direction and I'm going to get my two thiols back. So this step here, this oxidation and reduction, is used when you go into the salon and if you want to get your hair, have a permanent to get your hair curly, or the opposite can be true if you got really curly hair and you want to get it straightened. So how this works, and this is just for fun, we start off with this picture of this girl with straight hair, and hair has protein, so you have some of these disulfide bonds from that cysteine amino acid. So naturally you have these disulfide bonds in your hair. So here's our natural hair. You put on this solution, this waving lotion that contains an oxidizing agent. So actually I said this wrong. This part right here is going to be reduction because it's going to break the disulfide bond and put hydrogens on. So remember, adding two hydrogens means reduction. So the first step is to reduce the hair, reduce these disulfide bonds, put hydrogens on it. Then you put your hair in rollers. Sometimes you roll your hair first before you do this step. But you put your hair in rollers and that shifts the location of your cysteine amino acids. So you shift down some of your sulfurs into different locations around the rollers, and then you put on the oxidizing agent, which goes through and takes off the hydrogens and rebonds the disulfide molecules. So then when you take the rollers out, you now have curly hair because you formed different locations of your disulfide bonds. So that was just for fun. I'm not going to test you any questions on hair permanence, but I think it's kind of cool and fun.